Thank you so much for inviting me. It's a great pleasure to be able to talk to people outside UCSD. I'm very excited to present some of the new works I've done here, and I'm interested in hearing feedback from people. Yeah, let's get started. So the topic today will be learning to design soft robots. I'm curious for the audience, like how many people have designed a robot before?
How many people have designed robots before?
Oh, there are quite a lot. That's good. Um, yeah, so some of the or like how I was designing robots during my PhD, or I would say 90, more than 90% of people that's been designing the robot nowadays kind of start with a pipeline like this. We would CAD a design, it will open up your SolidWorks or your Fusion, you will draw something and pull off your mind, and then you will go make it. And then you will try to have a come up with a control policy that gets your robot to move around, do things as you want them to. And then you will just pray it will work. Sometimes it will just not work. Like you go ahead and try it, and the robot might mess up things, and nothing works. You get frustrated. So, um, it's a very big question of when we say robots doesn't work. Is it a issue of the control policy? Is it that the brain itself is not working properly, or is it the hardware that's just not getting it to work? So, um, when I came to use USSD as a post, that's kind of my topic for because of funding issues to make robot hands. I never actually worked on manipulation before during my PhD, so it's kind of a new area for me. Then I started to look for papers, and then I find this paper. It's a century of robot hands, which is pretty depressing, just because like you see how many people have made robot hands, and I'm just very confused of why people are still making robot hands. So I went and asked around for people that work on manipulation for some time, and they're like, because none of those hands actually works better than a gripper, which is very depressing because you spend so much time just working on complicated mechanical system, and it turned out to be well, you should just use a gripper. It's kind of a very depressing state for people that are actually making robot hands. So there's a very big gap, and I think that is, or from my perspective, that I think this was causing this issue, is the people that actually make the robot hands are generally mechanical designers, engineers. They're not the people that eventually use them. And sometimes the design goals and control goals might not be aligned. I think a lot of the robot hand nowadays, the goal is just try to mimic human hand. But maybe for if you are controlling things, well, having a human hand is good. But if you have a nod to the state of a human hand, it's not really the control goal of that. And another issue is, I think it's the lack of universal evaluation, because we make hands and we show, okay, they kind of works on this and that situation. But if we take another paper and look at other people's hand, it's very unclear how it compare with the hand I make in my lab. So that kind of brings in my topic today, which is learning to design soft robot, which is literally soft hand in this case. So for learning or machine learning, people will give this a classic definition is that machine learning is a computer's ability to learn without being explicitly programmed. So I give another definition of trying to learn and design is a hardware system's capability to adapt or have some emerging design parameter and behavior without being explicitly designed. Um, it's always a nice goal to have, say, like we want the control policy and the design just to be optimized together. It's a very nice goal to have. I see this work to be the first one that's actually doing like real code design. That's just putting control and design in the exactly same framework and backprop gradient onto both of them. I think the result is very interesting, but it's a good question of what is a design problem and what is a control problem. If you see like the baseline finger that is trying to push this block inside, the design you'll end up with is like if you have a bigger finger, you'll be able to hit the block earlier and you will be able to push it inside earlier. Um, I kind of feel like it's not really a design problem because technically the finger can push it inside if the control is like give it a faster command. So it's a very big question of what is a design problem and what is a control problem to be able to optimize them together. So in this talk, I will talk about two of the works I recently did. The first is actually doing co-design, but with a limited design and control space of face-off gripper. And another is after doing co-design for some time, I decided co-design is so hard. Let me just do pure design first. Yeah, so these are two works I'll be talking about today. The first topic, when we're trying to do um, computational design is to figure out a good design space. I started with the super simple flexure based soft finger that will just bend when you pull with a tendon. It's a very basic soft, like a flexure based tendon driven hand design. So if you see, I just put this tendon line uniformly uh, along this finger. When I pull it, it will always curl. I think if you see a lot of, I will say like 90% of the like fracture based fingers out in the papers have this issue that the fingertip will curl more and you only use the fingertip. So this is a design space we can explore as a tendon routing. And the second is for soft gripper, we definitely want to have different stiffness. Like if we have a very rigid finger, it might not be able to. I don't know why the video is so stuck. um, yeah, so if you have a very rigid finger, it may not be able to deform to the object you're trying to grasp. If you have a very soft finger, it's not very powerful that it can actually um, like grasp a heavy object. So this is another design space we're planning to explore is the stiffness values. For the first design space, it's not that needed for a computational, I won't say not compute for a like learning based method, just because we can technically derive equation that have all the finger pads to be uniform pressure, meaning that when the tendon pull, it will be able to just deform to whatever surface it goes onto. It's a pretty old equation which derives a uniform pressure along the finger. So in this way, if we pull onto it, it will be able to deform to whatever geometry you may want to have. Um, and then it comes to how we are optimizing for the design space of the stiffness. It looks like a very trivial question, but it's actually not, because for two finger, each of the if you for this each of the blocks I have 20, I have 11 stiffness values that I can tune. So, and each of them ranges very big. So it's actually a very big design space. So what we wanted is to have a very fair evaluation so that the designs are not optimized just for a single object or single category of object. So we run it on a huge data set, which is the YCB data set. It turned out to be the best data set, actually. We tried a lot of data set, but they have a lot of various issues with simulations. So what we did is we just sample all the designs, different stiffness distribution, as you can see here. Um, I don't know why it's not playing. Um, on on the entire data set, and we record the ending grasping force, ending grasping pose of the object, and if there's ground and object collision, meaning if it successfully lifted the object up. And we record these into, we compile this with a neural network. We'll talk about why we do that later on. But this neural network is conditioned on a lot of the things. First is the point cloud of the object and the center of mass of the object, the density, which represents the mass, and the stiffness that I'm sampling. So with this, I'll be able to compile a very fast feed-forward neurophysics model that represent the simulation of a very slow soft object simulator. And then we can generate, for this type of evaluation, we will be able to, okay, place. We can show that we can use it to evaluate sampled posts, and we can use it to evaluate sample designs. So with this very generalizable evaluation, we can quickly get the ending result of a grasping for the design and control combined. And with this one, we will be able to iterate through both the design and control policy at the same time. So how we are, okay. So how is this optimized? Well, for stiffness, it's a continuous variable, so we will do gradient descent and it won't mess up with the design space. And for control policies, we actually we tried to do gradients, but it's a lot of pain and actually doesn't work. So what we eventually tried was to have the control policy to be a library of sampled possible policies that's generated from external library and also the optimization. So with the sample library, we'll be able to just try it, and using this very fast feed-forward neural physics model to evaluate what is the best pose. And we pick the best pose and we iterate through this entire pipeline. So with this, why we're doing this neurophysics is we started from using, if you're familiar with it, a differentiable simulator, which is something that gives you gradients, whatever things you put in there. It sounds like a very nice tool, but it actually works pretty bad, especially for context. And the gradient gets very unstable. So what we did for this neurophysics model is this train network has really smooth gradient, and it can kind of drive your design and control policies to a better local minimum, basically. And what's also interesting is that once we optimize on the entire data set, the overall performance actually improves, meaning that the gradient from other object actually helps put each individual object gradient to be able to get out of local minimum. So overall, we actually get a better design that works on the entire data set. So how does the resulting design look like? I would say it's pretty interesting because first it's asymmetric. I think humans like to design symmetric things. And another is one finger will be, the fingertip will be rigid so that it kind of holds the object load. And the other finger is relatively soft and it will be able to kind of deform to the shape of the object when you're grasping. Some of the results we have in simulation here, it shows that the optimized design works better. I think it's playing. And this is on a out-of-domain object. It's a random turtle thing we find online. And we can also use this for neurophysics model to sample the candidate poses. For example, this shows that the pose that sample through the neural networks actually works better. Um, how it transferred to the real world, it feels like sim to real gap is always a big thing that people talk about. So, how we kind of realize this different stiffness is basically through different 3D printing parameters. For the flexure blocks, like the thinner ones, we can kind of change the number of inner layers in each of blocks to have different stiffness. And for the bigger blocks, we can change the infill type, the infill orientation. That will give us different type of stiffness. So it will look all the same from the outside, but it has different internal structures that give me different stiffnesses. And this is how it works on the real robot. We kind of show that with an optimized gripper, it works so much better compared to first a rigid gripper, which most of the people use, and another is a purely soft gripper that we initially started as a baseline design. Um, and it's a very like grasping irregular shapes with just a lot of the very standard method or with a rigid gripper is very hard. But with the uniform pressure equation we derive, it actually deforms to a lot of the shapes automatically. So it's a very nice feature to have. Some of the metrics, it's not that interesting to look at numbers. Um, for a simulation, we will say optimized gripper on the entire data set kind of always perform better. But we notice that for out-of-domain objects, like post-sampling is not that accurate, I would say. I think partially because the poses are very sensitive to the geometry still. And I think just training on the YCB object, which is like 50 or like 60-ish objects, is not that generalizable. The success rate on the real object, most of them are better, but actually for some of them, like the very regular shapes, the rigid one still works better because they're very round. So if you're not grasping onto the the exact symmetric lines of this object, it kind of fails. Some of the takeaways of this project is I think control and design happens in different dimensions. Just trying to naively gradient descend onto both of them at the same time might not give you what you want. Um, and another is sample discrete parameters like the the control library, and also use gradient descent on continuous parameters. For example, the stiffness is a much stable thing to work with. Another interesting thing I find is that joint optimization works much better. I think there are a lot of work that's doing just computation design on very specific object or object category. We feel like if we are able to generalize enough, we can actually get a general design that works across multiple objects. And there are things I don't really like. Of course, we always show the successful cases, but we are trying to play with this egg that soft gripper uses a lot of the time. It doesn't work very well. Like if you see, I don't know if people can see it clearly, but this gripper, the uniform one that deformed to the shape, it will deform to the egg. But if the pose is not perfect, it will just push the egg into the ground instead of just lifting it. So um, when I started this project, we really wanted to do geometry because that's what looks interesting. But deforming soft mesh inside a simulation is such a painful thing. It's not very solvable at the time we were doing. And the next is we don't really like this uniform pressure. It's nice that it deforms, but not really to the way we want it. And the performance of the grasp is just heavily bottlenecked by the control, which has a larger sim to real gap because of the real point cloud and the point cloud inside the simulation. Um, yeah, before I move on, is there any questions?
So how did you simulate the uniform pressure thing?
Um, so it's kind of just uh oh, I actually don't have it in the slides. So when I put simulate this tendon is a bunch of soft blocks and I apply this tendon model inside the simulation, and if I just change the position of this mounting, it will give us different behaviors, and for the soft one, it will deform like this in simulation. That's kind of how you see it here.
Do you think it's realistic?
Um, I think to some extent it's realistic. At least the deformation kind of looks correct. Like if I implement the uniform pressure, it won't curl at the fingertip. So to that extent, it's realistic. I think the deformation part is actually easier. I think that what's making the simulation problematic is really the contact. I think the contact model is very bad.
Yeah. So this is what simulator this is?
It's called Warp. It's from NVIDIA. They release it.
Oh, for
Um,
soft deformable.
it works with rigid too, but they kind of abandoned the simulator this year and decided they want another simulator called Newton.
Okay.
Yeah, but it's the same group of people. They just like new simulators.
Okay. It's yeah.
Um, cool. If there's no question, I will move on. Um, So the question that we're trying to answer is what is needed to generate good designs? I think for the previous project after this trial of doing code design, there are a couple things I think are very important. First is some ways to stably update the designs that won't explode the simulation, it won't explode anything. What we did for the previous project is we separated into continuous parameters and discrete parameters. We do gradient descent onto continuous parameter. And for discrete parameters, we just sample it. And we really need a very good evaluation metric that can be generalizable um, throughout the entire data set, not just optimized for single objects. Um, and the next is we need a good control backbone to put designs into action if we're actually doing code design. For what I did is the controller itself is kind of based on the rigid version of the gripper. So that's kind of generalizable cross design because the shape doesn't change. And ideally, they can also improve along with the designs. That is something that we find to be interesting because given a library of the control policies, with the neural network, we can condition them on the stiffness distribution so that we do get a design that works better condition on each different, um, uh, get a control that works different and conditioned on the designs. Yeah. Um, so our next trial is we really wanted to do geometry. I think having grippers that looks all the same is not really fun. And we want a very efficient way and stable way to do geometry. And I realized just a lot of the previous issues were actually with the control policy. And I kind of just want to get away with that with teleoperation, which is a lot what like people do nowadays, just to get away with good teleoperation data. So we changed the two finger to a three finger, And we changed the design space to be wider, which include the tendon distribution because we didn't like the uniform pressure one. And we can change the blocks, the length, the height of each of these blocks, and the mounting positions. It actually turned out to be a really big design space. So what we did is we kind of just collect data with a uniform and baseline design inside in the real world of different objects, and we replay it in simulation. We'll say most of them that fail in real world actually failed in simulation. Um, so what we did is we have an efficient way of sample the designs, which is a cross entropy based method where we model each design parameters as a Gaussian distribution, and we sample on top of this Gaussian distribution. And for each sample, so we'll evaluate the design. And then we will get a reward that's formulated exactly the same as our previous work if we successfully grasp it, the pose and the force on top of the object. And so soft simulation is very slow, and sampling designs, it will take a couple of days. So what we did is we train a reward model that is iteratively updating based on the sample designs that we put in there, and we iteratively increase the rate of using this reward model to get the evaluation of different type of designs. So with this kind of iterative, uh, was this kind of, I don't know why it's stuck. Yeah, with this kind of iterative method, we can get very fast and accurate reward models. I don't know what's happening. Very fast evaluation on different soft hands on top of this reward model. So how the optimized design look like? Um, so first is not symmetric too. The next is this thumb is kind of facing, I will call it the index finger instead of facing both of them. And the other is the index finger and the middle finger is kind of a little bit symmetric in their own circles. And another interesting thing is, although we started with a non-uniform pressure, it landed up to be a uniform pressure distribution that is kind of similar to the quadratic curve you see in the previous work. Well, I guess if that's optimized result, we should take it. The interesting thing is all the fingertips are really big because the force that you apply to the object is actually the moment arm is this, so that if you can see um my mouse, it's this. So that was a bigger moment arm. It actually applies more torque to the object, and that helps lift out object from the tabletop. So that's an interesting finding. And then we deployed this optimized design onto the real world. Um, and it does improve the baseline. Um, I don't know why it's so. Okay, so for the reward models, we can see that it actually helps to reduce the number of simulation we need to do. It almost reduces it half. That means that we can explore 2 times more designs inside the simulation within a given time frame. And for the sim to real success rate, we will say that we tested on 2 types of control, which is the first is just deploy the exact teleoperation pose we collected during the data collection. We'll say some of it improves. In general, overall it improves, but with a different design that if we ask the teleoperator to re-teleoperate it, and humans are actually great learners and they adapt to this design a lot better. So this is example case of how it's working. Um, So some of the takeaways for this project first is we noticed that design is way easier to transfer from simulation to the real world, like compared to the control policies, because it's not perception dependent. Although the exact forces and everything, it doesn't actually transfer. But if a design that works overall better in simulation is indeed going to work a lot better in the real world. And next is we notice that generating designs in a computational framework make it more accessible because if people don't know we should do the uniform pressure tendon routing or doesn't quite know how to do it, it's a good way to just have the framework to generate it, and that makes a lot of the things more accessible. Um, some of the ongoing works that we are currently doing kind of lies in the um three domains. Is we want a way to update designs that is useful and won't actually explode anything. So something I'm personally very interested is just modeling designs as the 3D printing path. I think that's a way more stable way to optimize design because mesh are very hard to work with. They're very annoying if you actually work on this. So with different geometry, this is a ongoing project that's making sensors. It's a purely 3D printed geometry that is conductive that can be used as a tactile sensor. And we are also working on a better pipeline to do real to sim alignment, mostly with tactile sensors, and hopefully they can actually give us more aligned physics model in the real and sim. And another thing that's very important is with the control backbone that we need to have a good control backbone to put designs into action. And this basically means we need a cross design control policy. So that is what we are currently working on, is to have a cross embodied control policy that work across different type of designs. Um, that is all. Thank you for having me. Please let me know if you have any questions.
Nice talk. Any questions? Yeah, please come forward.
I have a question about like the order of the session I must see. Okay. Yeah.
I
So,
I think the sound is kind of cutting off. Can you repeat your question?
Yeah, here's the mic.
yeah. Yeah. My question is like the order of sim and real. For example, I normally we use the simulation to design and then go into the real world. But sometimes when you like in the real world, you find a material, something that's really good, want to put it in your simulation or do something like that. So do you have any ideas like the what's the comfort, the sim and real thing?
Yeah, it's a very good question. I think I think people I don't really have a good answer. I think what we did is use a really good machine that get the material properties and put that in simulation. I think it helps a little bit, but I feel like the simulator framework nowadays are still very immature. Like NVIDIA put out a different simulator every year. So I don't want to say just don't do simulation, but I think just having a good way of using simulation and don't just directly use the simulation policy. Like use it in a good way that can be informative, but don't rely it too much, kind of.
Yeah, thank you. And, another question is like, wait, I forgot.
Okay.
Oh yeah, I see. It's like from the simulation to real is that there are many like randomization or like uncertainty. So is there like a like what I want to ask, what's maybe from your observation or experience, what's like the gap between sim to real, and also is there any like more scientific or mathematic way to like to I don't know, like model this randomization or uncertainty?
Yeah, so in our first work, we actually use point cloud, which I find to be have a much smaller sim to real gap. So, and inside simulation, we can add a little bit noise to the point cloud, and that kind of makes it work a lot better. So I think visually it will be really hard. It's a very big vision people question. But I think point cloud worked a little bit better. As for scientific ways, so there are a lot of work that's doing kind of you do a lot of domain randomization in simulation, meaning that you just randomize a tons of parameters and hopefully they cover your real world distribution. So that is another way of doing it. And there are quite some work that's doing that line of experiment. Yeah.
Thank you so much.
Any other questions? I actually have a question about like what other design problems you are interested, like especially co-design problem, you think that are both interesting and practical, which have like real application value.
Yeah, I actually like this ongoing work a lot, which is although the design space is still kind of small, but I'm a little bit annoyed by the soft robot community because everything is not ready. So that's why I kind of started working on rigid things. I personally think, although we still haven't released this work, but we submitted it. I think just coming up with good design space that you think will be more impactful will be great, that can kind of really generate useful design. So some of the things we find in this work that so for this one, we are just randomizing, or not randomizing. The design space is the number of fingers, the mounting position, and the link length. We add the fingertip shape. We actually notice it to be a lot interesting compared with just the pure soft bodies. Another, I think because it's so much different, like the design space need to be um big and diverse enough, and it needs to be not exploding things. Yeah, I think for now it's a lot more intuition you put into the design space. If you come up with a really good design space, I think it solved half the problem already.
Okay, another question is about your sensorized object. I'm not sure if that's still the name of your project. But can you
Yeah.
talk a little bit more about like about this? I'm actually very interested in how would you use it as like a path.
Yeah, so yeah, we talk about the sensorized object because I find this 3D printing material very interesting. So it's conductive and it's something you can buy just off the shelf. And you can print it with whatever 3D printer you have. Um, so how it works is basically it's basically a huge resistor that if you press onto it, it will short circuit this area and it will give you a different reading. So I think just printing for a lot of the object data set, you have the mesh. I think if there a way to just get the shell of the mesh and insert something inside it, it should be able to give like a sensorized object. But that project's not going anywhere. And my two PIs are not actually interested. So if you're interested, I'm happy to provide feedback on it if your students are interested.
But what if you put it on fingers? Do you think
Yeah,
makes
I
sense?
think, yeah, so this was designed to, we have a 3D version of this. It's a black thing. You can't see anything inside of it. But yeah, this can be a fingertip. And it's a very, I don't know how it really compare with other tactile sensors, to be honest, but this one is just really easy to make, um, compare with others. And you can define different geometries based on what you want. Yeah. It will work, but it's a binary signal though.
Yeah, I'm also curious if you, I think you already have the differences in the shape. Does
Mhm.
that, I mean, if you have different shapes that are connecting, does that give you different resistance?
Yeah, so it gives you different resistance. So in this finger, we can actually have relatively good spatial resolution. So it can
Yeah.
differentiate between pressing here, here, and here. So, but we notice this is actually twice your finger as big as that. It can only differentiate like 4 spatial resolution just because there's just so limited space. I think there's a ways to still optimize it. But yeah, this is an undergrad project and it didn't really go anywhere for now.
Yeah, maybe you can use the co-design to design the shape and the of those.
Yeah,
Not sure if that's possible.
I think it's possible. It's just I'm not an expert in mesh, and mesh is just so annoying. I think geometry is very hard. I think I need a good computer graphics person to help out on the project. Otherwise, I don't know how to update mesh in a very good way.
Okay, cool. Yeah, is there any other questions from the audience? If no, let's thank Yusha again.
Thank you. Thank you for having me. Yeah, feel free to reach out if you want to talk about things.
Yeah, thank you so
Okay.
much. Yeah.
Thank you.
Okay, see
Bye.
you. Bye.